Good morning and good afternoon, everyone, once again. Thanks so much for joining. This is our third webinar here at IWC in a recurring series we're calling Wired for Success. And today's topic is entitled Wire and Cable 102. Yes, there was a 101 back in about the August-September timeframe, which hopefully many of you are on, and if not, it's certainly available online as well. But today we're covering a 102 level topic, which is looking at wire and cable for looking at the basics of conductors and insulations and others there. And so really it's meant to be a high-level overview as well of some of the various approval agencies that you'll likely see as you research and purchase various materials in the wire and cable space. So my name is Dave Burleton. I'm the marketing leader here at IWC. I'm excited to be with you here today, and I'm going to serve as the moderator for today's session. And I'm joined once again by our presenter, Matt Herbers. He's our Director of Business Development here at IWC. Now, in that role, Matt has visited hundreds of wire and cable production facilities around the globe. In that role, he spent a lot of time matching the application to the supplier resources for our customers. In addition, he also heads up our technical training program here internally within IWC. So he's excited to share some of that same training materials with you here today. He's a proud alum of Northwestern University, and he has more than 30 years experience working both with manufacturers and at distributors. And that experience spans procurement, sales, and management. Now, allow me just a moment to share a bit about IWC for those of you who may not be familiar with our organization. For more than 55 years, we've been an entrusted partner for thousands of companies in manufacturing, in infrastructure, broadcast, telecommunications, and some other industries. We're an employee-owned company. We've got about 30 locations in 11 different countries, and we serve customers in nearly 100 countries around the globe. Now, before I turn things over to Matt to begin the presentation, allow me just a few minutes to share a few logistical details, just to ensure that the session runs smoothly for every one of you. Now, first of all, we are recording this webinar, and we'll make that available to each of you so that you can revisit the content of this webinar at any time. So keep your eyes peeled. You'll see an email over the next few days to let you know when that's available and how exactly to access it. Secondly, to ensure a good audio experience for everyone, we have muted the phone lines for everybody but the presenter. So what I would do is I'd encourage you to make use of the questions window within the webinar over on the right side to submit your questions and reach out to the team here throughout the presentation. Thirdly, this is a live webinar, and we'll be offering a question and answer session at the end of today's call. Now, as I mentioned, the phones are going to be muted, so we will have you submit those questions through that chat window on the right. So no need to wait till the end to ask your question either. If you have a question that pops up at any point in the presentation, go ahead, share it with us through that chat. We will get through as many questions as we can on the call. If by chance we run out of time and are unable to address your specific question, rest assured, because each and every submission will get a direct response from the presenter via email. Okay, enough logistics. Let's get started on the presentation. All right. So at this point, let me hand things over to Matt to walk us through the details of today's topic and the agenda he has prepared for you. Matt?
Well, good morning. Hello, everyone. I'm good morning here in Milwaukee. Good afternoon, where you are. So our agenda has 3 points. We'll talk about conductors, insulations, and then a little bit about the approval agencies as well. So there's a little bit of data that we're going to be going through here. So let's just jump right into it. Wire and cable 102. Here's some of the things we're going to be talking about. Why is the copper conductor better sometimes, and other times you use aluminum? Does stranding really matter? If it's 16 strand or 65 strand, does it really matter? And sometimes your engineer is going to call out a tin-plated copper conductor and sometimes bare copper. What's the difference? Who cares? What does it matter? And then finally, you know, a lot of the polymers are just one acronym after another. I'm going to give you a few hints when you see an acronym that'll tip you off about something about that polymer that'll be quite useful to you. So I call that the alphabet soup of polymers. So let's just talk about conductors right now. So what would be the primary difference between a conductor and an insulator, right? One conducts, the other one doesn't. So the biggest single difference is really simple: free electrons. All right, free electrons, very nice. What does that mean? Well, here's a picture of a copper atom right here. And as you can see, there's one electron hanging out there in the outer shell. Now, that is the free electron in this case. And metals, all metals have free electrons. It's what helps the metal stay together. Those free electrons keep the metal together so it doesn't turn into a gas or a liquid or anything else. And it also allows for conductivity. In the case of copper, you see it's just got that one little electron hanging out there in the outer shell. And I'd say it's looking for excitement. In fact, when it does get energized, it's called an excited electron. And that's what makes copper so very, very good. There's that one guy just hanging out there alone, all right? Insulators, on the other hand, like a styrofoam cooler, for example, or like PVC that goes around your conductor, does not have any free electrons. All of the electrons are paired up. They're all in their shells. And what that means then is that they're less likely to conduct. All right? So what's the difference between conductors and insulators? There you go. How do we measure a conductor? Largely through resistance. So often you're going to hear resistance called out. Let me just talk a little bit about what resistance is. First, it's how we measure the conductor, as I said. Now, electricity moves through conductors at different rates. Some of them resist a lot, and some of them don't resist so very, very much. When you think about resistance, when an engineer talks about resistance, just picture in your head what it's like running through a pool of water. That water is resisting your ability to run. And so it is with a conductor. It's resisting the ability of electricity to flow through that conductor. What you want, a good conductor has less resistance. It's easier to run through that medium. All right? So let's just take a look at some common resistances of common conductors. So you can see on this table, silver is in fact the very best conductor that's out there. It has the lowest resistance. I'm going to tell you later on in the presentation that copper is the better conductor, and I mean it's better because it's cheaper than silver, but in fact silver has better resistance. So in this case, silver has 16 billionths of an ohm per meter. Copper is 17, and then gold and aluminum. You can see as you go down the chart how different metals resist differently, and that's why you're going to choose one product over another. You can see silicon all the way at the bottom. In fact, that's a semiconductor. All of your solid state materials in your computer use silicon because it's a semiconductor. It conducts sometimes, it resists other times. That's a different story. We won't get into that today. But anyway, you can see the difference between, in this case, copper and aluminum and iron in terms of conductivity. All right? So the two basic conductors that are used for commercial purposes are, and I guess most of you can think of the first one, which is copper, and the second big one in the commercial world is aluminum. So I want to talk, the conversation will be addressed towards these two primary conductors today, and I'm going to start with aluminum. So aluminum has three key advantages that makes it a good conductor. Number one, it doesn't weigh very much. In fact, it only weighs 30% as much as copper. So a 6-gauge aluminum weighs a lot less than a 6-gauge conductor of copper. Number two, aluminum is inexpensive. It's considerably cheaper than copper. In this case, you can see it's about 1/3 the cost of copper. And then number three, it's a pretty good conductor. I was showing you the resistance before. It's not as good as copper, but it's a pretty good conductor. And so it's good for moving that electricity. So let's just take a look about how good it is as compared to copper. So in 8-gauge, you can see copper can carry 55 amps and aluminum 45 amps. And then as the conductor gets bigger is where it gets to the more standard difference between aluminum and copper. These values, by the way, are all per the National Electric Code. But generally speaking, aluminum has 70% of the current carrying capacity as copper. All right? That's just the number that engineers walk around with in their head when they're comparing aluminum versus copper. So I'm going to take this just a little bit further. So this is the current carrying capacity. Copper can carry more electricity. What about weight? Well, look at the difference in weight of the 8-gauge, for example. Copper weighs 53 pounds per 1,000 feet, and aluminum only 16 pounds. And of course, you know this, you pick up something aluminum like a soda can, and it's lightweight, right? And it stays that way throughout the size of conductors. So about 30% the weight of copper. Well, let's take a look at the cost then. How does this, let's take, I want to compare, I'm going to use a conductor that carries 75 amps. I don't care if it's copper or aluminum. I just want a conductor. Your engineer is thinking this in his head. What size conductor am I going to use? Well, in copper, if you want to carry 75 amps, it's going to take a 6-gauge conductor. And that 6-gauge copper weighs about 75 pounds 1,000 feet, and it costs about $2.75 a pound today. So that conductor costs about $206. Just a conductor. No insulation, not anything else, just the copper conductor. How about if we do aluminum? Well, if you remember aluminum, you need a larger conductor to carry the same amount of electricity. So the 4-gauge aluminum is bigger than the 6-gauge copper, but it's going to carry the 75 amps. Let's look at that cost. Aluminum, even the larger conductor, only carries 40 pounds, or only weighs 40 pounds per 1,000 feet. It's only 95 cents a pound. So look at that. To carry the same amount of electricity, aluminum is $38, and the copper is $206. Well, for crying out loud, let's use aluminum. Who needs copper? Let's use aluminum on everything. It's that much less expensive. Well, aluminum has its limitations. And those limitations are what are going to explain why an engineer is going to specify one over the other. Here's a limitation for aluminum. Once you get much smaller than 8 gauge, it's really difficult to draw that aluminum conductor down to a smaller size. Aluminum gets quite brittle and will break. It isn't that you can't. You can get smaller than 8 gauge, but it gets progressively more expensive as you get down to the lower sizes of aluminum. Number two, aluminum is simply larger. So if you're in a tight space, like think about a motor that you're using in a hair dryer, for example. You want to dry your hair. You don't want a big hair dryer. You want something you can hold in your hand. Aluminum is physically larger, so that appliance has to be bigger to accept that larger space. Also, aluminum is not as flexible as copper. So if you've got a tight bending radius, say in an electrical box, copper can get in very tight spaces, and aluminum simply doesn't bend as well as copper. So you need a bigger appliance or a bigger electrical box. And then finally, aluminum has a characteristic as it heats up, the aluminum expands, and as it cools down, it contracts. Copper expands and contracts very, very little. Aluminum, more so. As a result, the connectors used on aluminum have to be able to expand and contract as well over the lifetime that they're being used. So you can imagine that type of connector, which is flexible with the conductor, is going to be more expensive. So aluminum then is limited in its applications, but there are some places where aluminum is simply the perfect conductor. And the best example is power cables. You drive down the side of the road and you see all those power cables. They're all aluminum. You can see them. They have that silver color. That's bare aluminum that you're looking at. Well, it's lightweight, so it's easy to string over long distances. And because it's lightweight, it won't sag over the life that it's hanging there. If it were copper, copper is going to sag as it stretches out over time. Aluminum won't. Another example, aluminum is perfect where fuel efficiency is something that you're really concerned about. And so aluminum is being used on more and more car batteries. If you buy a Mercedes-Benz or an Audi right now, and you open up the hood, you take a look at that battery cable, it's aluminum. The reason that, in fact, it costs less than copper, but for Mercedes and Audi, also BMW, it's the weight efficiency that's driving that consideration for those manufacturers. And so GM, Ford, and Chrysler are also looking into aluminum battery cables now. So aluminum is perfect for a lightweight situation. It's also perfect where the space you have is unimportant. So you think about cables that you see buried in the ground. In my subdivision where I live at home, we don't have any power lines. All of those cables are buried in the ground. and almost all of them are made out of aluminum. So space is not a consideration. You're going to use aluminum. It's less expensive. If you do see power cables running into a factory or into a commercial building, so many of them are also aluminum. And again, it's because it's up in the air. Space is simply not a consideration. So you can use aluminum. So those are the advantages of aluminum. That's when an engineer is going to specify aluminum. All right? Let's talk about copper. So if aluminum has advantages and limitations, copper also has some advantages. Number one, it's a very good, it doesn't resist electricity going through it. It's the best conductor, and I call it the best because it's readily available around the world. You find it in Mexico, in Poland, in Turkey, in Russia, in China, in the Philippines, in Australia, in the United States. So you got copper around the world, and it's relatively inexpensive, and so it doesn't resist electricity. Number two, copper can be stretched like a rubber band. It's hard to imagine, but if you pull copper through a small hole, through a die, you can get that copper smaller and smaller and smaller, and it stretches so that you can start with copper that is 5/16 inch wide, about the size of your small finger, and it can go all the way down to a 50 gauge copper, what I call angel hair. It's so thin, it's thinner than a page in your notebook, which means you've got the advantage then that copper can be drawn down to small sizes. So let's just talk a little bit about drawing that copper down. When we draw a wire, you might have an engineer that says it's got to be drawn to a certain size or to a certain strand count. Really, all that means is that you're pulling that copper through a series of dies and reducing the outer diameter. All right, what an engineer will call OD. You'll see that on a lot of drawings. OD. It's just the outer diameter of the conductor. So as copper is drawn down, as you're running it through that die, I'm just going to go back to that picture. As you run it through that die on the bottom right there, as you draw that down, the copper becomes harder and harder. It forms crystalline structures. So what that means is that drawn copper needs to be heated up again. There's a special word for it called annealing, and it's just a word you're going to have to learn if you're in the wire and cable industry. That drawn copper is annealed to make it less brittle, to take those crystals out of it, and it becomes more flexible. If you don't do that, the copper becomes really brittle and it will break, and it's a problem. So you're often going to hear about annealed copper, and all that means when you hear annealed, it just means it's been heated up. That's all. Just a special word used in this industry. All right. So you're going to see copper can be purchased either as hard drawn or soft drawn, and all that means is it's been annealed or it hasn't been annealed. There aren't too many times you're going to buy hard drawn copper, but you might buy hard drawn copper. It might be specified by an engineer, and all that means is that it's the size we need. We don't need it to be any softer, so it's going to be less expensive than soft drawn. All right. Whenever you see soft drawn, you can immediately imagine more expensive. Hard drawn is cheaper because it hasn't been heated yet. All right. These are just little clues when you hear these those terms. So okay, we're going to turn into strands. Does stranding really matter? You know, does it really matter? For example, these are all 16 gauge strands that I have here. The most common that you're going to see is the 26 strand. The 16 gauge 26 strand is called out all the time. And you're going to see it on a drawing as 26/30. That means there are 26 strands of 30 gauge copper. All right, I laid it out above in the 7 strand, 7/24, 7 strands of 24 gauge copper. Well, the 26 strand is called out the most, 26/30, and the 30 gauge copper has a width of 10 millinches wide, so 26 by 0.010 inch copper. That 10 millinches is also called 10 mils. You might hear someone say, oh, it's 10 mils thick. That's all it means is 10 thousandths of an inch. If you look at all these strand counts, whether it's 16 gauge, whether it's solid or 26 strand or 65 strand, they all have about the same OD. They're all about 51 mils wide in their outer dimensions, which means they all have about the same resistance. There isn't that much of a difference. So if there isn't that much of a difference, why would you go with 65 strands? Why wouldn't you just go with 26 strands? Well, the reason that your engineer is going to call out more strands is you get better flexibility. The greater the number of strands, the more flexible the conductor. And you might need it to be flexible because it's in a very tight bending radius. Or maybe you don't need it to be flexible at all. There's a lot of solid strand conductor that is used in between walls of the building that you're in right now. You put it in the wall and you're finished. You don't need it to be flexible. It can be inflexible and it holds its position. All right. So you're going to have greater strand count if you need more flexibility. But here's the deal: the higher the strand count, the greater the cost. So when your engineer says we need better flexibility, you can hear, okay, your cost just went up. It's like, okay, we use solid conductor. Okay, your cost just went down. So flexibility means it's greater cost. You also lose a little bit on the resistance, but not too much. So you don't need to worry too much about resistance when it comes to flexibility. But occasionally someone's going to say, we can't accept that conductivity. We're going to need a lower strain count to get the resistance. Doesn't happen too often, but it might come up from time to time. All right? The higher the strain count, the higher the cost. So I said that aluminum has its limitations, if you remember. Copper also has its limitations. One of the biggest limitations you're going to see is oxidation, right? Copper, as it's exposed to oxygen over its lifetime, will develop, there'll be copper oxide on the very exterior, on the surface of the copper. And as it oxidizes, it has less conductivity. In this case, this copper structure doesn't need conductivity. It's made copper maybe because of appearance or for whatever reason. But copper does oxidize when it gets into high heat. Copper is very sensitive to heat. And the more it oxidizes, the more exposed to the high temperature it is, the more it will oxidize, and it will begin to lose its conductivity. It will begin to get higher resistance. So what do we do about it in the wire and cable industry? Well, to resist oxidation, we put plating on the conductor. We'll have a strand that is tin-plated copper. Surely you've seen this. It's called tinned copper. It's called tin-plated copper. And the advantage is that now that same conductor can be used in hotter applications. Tin-plated copper can be used in applications up to 175 degrees. If you need to go even hotter than 175, you'll see silver-plated copper. And even above that, sometimes you'll see nickel-plated copper. So the reason that you have tin-plated copper or silver-plated is all about heat. We're trying to resist the oxidation to the copper. All right? So the problem, of course, is with each one of those, your cost goes up. Tin-plated copper is more expensive than bare copper, and silver more than tin, and so on. All right? So whenever you hear plating, same thing, think higher cost. Now let's just talk a little bit about those coatings. In addition to reducing oxidation, there are other advantages. So let me look at those platings again. The common coatings are tin, silver, and nickel. Those are the three you're going to run into the most. But in addition to reducing oxidation, tin plating also has another advantage, and that is that tin has excellent soldering capability. So if your application, if you need to solder that conductor, say to a printed circuit board or to anything else, the engineer will often call out a tin-plated conductor. In this case, it's not about heat, it's about getting that perfect electrical connection. And tin-plated copper is better than bare-plated copper. Or, if you remember, I said that silver has slightly better conductivity. In some high-performance data cables where you've got to transmit a lot of data in a very high speed down a conductor, you're going to use silver-plated copper. So it's not just about heat, it's also about transmission, how we need the best conductivity available. And then occasionally you're going to see gold plating, like in a computer. If you open up your computer, you might see some gold-plated terminals there. In that case, gold plating resists corrosion of any sort over the time. So that's the only reason you're going to use gold plating, so you don't have corrosion. It's doggone expensive, as you might imagine, so it's not used too often. All right, so that's why you're going to see different plating, different coating. So every conductor is going to have its limitations, whether it's aluminum or copper or any other conductors you're going to use. There's thermocouple, there's all kinds of special conductors you're going to use. There are limitations to those copper conductors. And the perfect limitation, we all run into it, is if you plug in too many light strings on your Christmas tree, the extension cord can get hot, right? It's just you're demanding too much from that conductor, and if it gets too hot, we can start a fire. That's not a good thing 1 week before Christmas. So what do you do then about an undersized conductor? Well, doggone it, you got to get a larger conductor. So you go to the hardware store, and instead of an 18-gauge extension cord, which is the cheapest, maybe you need to go to a 16-gauge extension cord because you want to run that many lights. Or if you're like the guy from Vacation, I don't remember his name right now. Dave, do you remember his name? What was his name from Vacation?
No, I'm blanking as well. Yes. Griswold.
Griswold, right? The Griswolds. Remember, he didn't have enough power in his extension cords. You can start a fire. Anyway, sometimes you just need to use a larger conductor. So there are disadvantages of going to a larger conductor, though. It's more expensive, right? You got more copper in it. It's bigger. It takes up space. What if I don't have a lot of space? It weighs more. What if I want something that's lighter weight? So how can I get more electricity through the same conductor? Well, this takes us to insulation. The answer is insulation. Really? How can I get more electricity through the same conductor? Well, different insulations have different properties. So let me just give you an example here, and then we're going to go into it a little bit. If you buy an extension cord at the hardware store, and it's made out of PVC, you can run your Christmas lights, or anything for that matter, doesn't have to be Christmas lights, but you can run your lights outdoor, and you can run up to 15 amps in that extension cord. That's your 14 gauge, no problem. Well, if you buy a 14 gauge wire, THHN, which is commonly used in between the walls of any building, that's rated for 90 degrees instead of 75 degrees. Since it's rated for 90 degrees, you can run more amperage through that conductor. It can get a little bit hotter. So you can run 25 amps through that. It's because you're using a different insulation. It's PVC with nylon on the outside, and it's rated. This PVC is specially built for 90 degrees. Well, there's another kind of PVC called irradiated PVC, which is made through irradiation with an electron beam. I'll talk about that in a bit. And this can actually go up to 150 degrees. So that's a UL type 3271. I don't know if you've ever seen that type of, that UL style called out. But if you can go to 150 degrees, that means you can run 40 amps through it. And there's even another one on top of that, which is a cross-linked polyethylene. You can go up to 200 degrees centigrade, and you can run 45 amps through that. So your engineer might say, well, we need to run 180 amps, or excuse me, we need this to go up to 180 degrees C, and we can run 40 amps through it, or 45 amps through it. So all these are the same conductor size. It's all 14 gauge. But because you're using a different insulation, you can run different amounts of electricity through it. Now, as you might imagine, the insulations get more expensive as you go up that ladder from 75 degrees to 90 all the way to 200 degrees. It gets more expensive. All right. So I need to talk just a little bit about the two major classes of insulations. And if you walk away with anything from today's webinar and you remember this, it will have been worthwhile. The two primary types of insulations are thermoplastic and thermoset. Thermoplastic and thermoset. Thermoplastic has that word plastic in it, and it means it's pliable. It's going to melt. It can. It's very It can change shapes very easily. Thermoset means that it is set forever, and it doesn't change. Sometimes you want it to change, like in a plastic case. Sometimes you don't in a set case. All right? Buckle up. We're going in. We're going back to high school chemistry, everyone's favorite thing to do at 10:30 or 11:30 in the morning. So when we talk about thermoplastic insulations, and PVC is a very, very common one, you apply heat to that PVC. You take it at room temperature and you apply heat to it, so it's going to melt. Well, as it heats up, those carbon chains begin to slip and slide, which means that they flow, and that's what you want. You want it to flow, all right? So thermoplastic carbon chains will flow. The other kind, which is the thermoset, is a cross-linked molecules. And as you apply heat to these carbon chains, instead of flowing, they start bonding with the carbon chains next to them. And you wind up getting this hot mess of carbon chains that it doesn't matter how much they heat up, they're not going to flow. They're not going to melt. They're not going to move. That's called vulcanization. So the tires you use on your car have all been vulcanized. They're all made up of cross-linked molecules. So it doesn't matter how hot that tire gets, it's not going to melt. Now it'll burn, any polymer is going to burn, but it won't melt. And that's the advantage of a thermoset material. We often call this cross-linked. When you hear cross-linked, it means it's cross-linked at the molecular level. All those carbon chains are linked to each other. All right? So there's your high school chemistry. So why would your engineer say, I want a thermoplastic? Or why would she say, I want a thermoset insulation? Well, she might say, I want a thermoplastic because, doggone, it's cheap. It's inexpensive. Or because it's easy to manufacture. It's also easy to mold. And thermoplastic molding goes around thermoplastic insulated cables quite well. They bond really, really nicely. And it can melt and be reused. So it's recyclable. It also has the advantage if it after you use it once, you can use it again on the bleed out that in the initial production. Okay, but now your engineer says, you know what, we need something thermoset. Why would you need something thermoset? Because it's never going to melt. So if you're in a high temperature application, go to your car today and open up the hood and look at the wire underneath the hood. Almost all of that is thermoset material. Why? Because it will never melt. If that wire leans up against the engine block, it won't melt. It will stay intact. So it's perfect for hot applications. All right? But the only problem with thermoset is that it's expensive production lines for the wire and cable manufacturer. If you're going to apply that thermoset insulation over the conductor, it's expensive, which means a large investment is required by the manufacturer, which means a relatively small number of manufacturers can do it. So everybody can do thermoplastic because it's not too expensive to get into production. But thermoset is only, it's a smaller number of manufacturers who can do it because the investment is so high. All right? And then finally, the base chemicals in thermoset are more expensive. So when your engineer comes to you and says, we need a thermoset insulation, you can say, okay, that's going to be more expensive. When you hear thermoset, think high temperature, think expensive. You hear thermoplastic, think it can melt, and it's less expensive. Now, and then here's just a visual. Thermoplastic, you remember I said when you heat it up, they can slip and slide. So that's what spaghetti is like, right? Before you cook it anyway. Those noodles are hard and they're rigid, they're firm, they don't really get all mixed up together. But the thermoset would be after it's heated up, it gets all goopy. And those thermoset those thermoset polymers I just say they get goopy, they just get all linked together. They get linked across each other, and it's impossible to extract them by heating it up again. All right? So I just want to talk a little bit about one of those conductors, one of those insulators, that's thermoplastic. When they're commonly used thermoplastic polymers. You'll see it, PVC, polypropylene, polyethylene. You're going to hear those called out. There's another kind called Teflons. Your engineer might call out an ETFE or a PTFE or a PFA. Whenever you see an F, this is part of that alphabet soup I was talking about. When you see an F, that means Teflon. Just think Teflon immediately. You know what else you need to think when you hear Teflon? Think expensive. So whenever your engineer is going to call out an ETFE or PTFE, PFA, that's going to be an expensive product. That F is a fluorine, the chemical in it is fluorine. So it's expensive. One of the advantages of Teflon, though, is it's excellent in high temperature applications. It doesn't melt easily. It has to get to extremely high temperatures before it's going to melt. So it's used in military applications a lot, in aerospace applications a lot. Also, Teflon is used in medical applications. Think about, you know, your non-stick Teflon frying pan, any type of cable wire that needs to put into your body, such as when doctors use cable with a small camera attached to it, is generally made with Teflon insulation because it doesn't stick to anything. It doesn't react with anything in your body. So Teflon is expensive and perfect for certain high performance applications. So I talked about thermoplastic. Now I want to talk about Thermoset. Remember, this is the one that's set. It doesn't melt. So your engineer is often going to call out chemically cross-linked insulations. They'll include XLP, XLPO, XLPE, EPDM, rubber, SB. Really? So many different names for the same thing? Whenever you see XL, that is an acronym for cross-linked, right? So they're cross-linked materials. So when you see an X or an XL, you can immediately assume that that's cross-linked, that it's thermoset, which means what? High temperature, high cost. All right? Now, unfortunately, it's never simple. There's another class of thermoset materials, and this is called irradiated cross-linked materials. And it's irradiated through a nuclear electron beam that is literally bombarding the insulation. So it has to be done in a special irradiation chamber. These chambers are big. You can walk into them. They're expensive. So there aren't that many folks out there who are doing this. But through irradiation, you can also get the cross-linked material. You can also get the cross-linked insulation, which means, as I said earlier, those carbon chains link across each other. All right? So it's a huge investment to use the nuclear electron beam, but it has some special characteristics that you're going to need in an application. That's the only reason someone's going to call it out. It requires the Nuclear Regulatory Commission approval. Again, that means it's expensive. So I'm just going to go back there. If ever you hear irradiated cross-linked, think expensive, all right? But it's also very special applications. It's used a lot in automotive applications where high temperature is critical to the performance of the product. A perfect example is where it's used in anti-lock braking systems. You might see ABS systems are almost all electron beam irradiated cross-linked materials because they can get to extremely high temperature and never melt. And boy, you don't want your brakes to fail, do you? And so you're going to be using these electron beam cross-linked materials. Okay, then there's one last insulation you need to know about. It's called low smoke zero halogen. We're getting to the end, folks, not too much longer. So low smoke zero halogen. Low smoke, you're going to hear abbreviate LSZH, LSOH, LS0H, for crying out loud. There's a lot of abbreviations for the same thing. All that means, or excuse me, all polymers can burn, whether it's thermoset, thermoplastic, and they emit smoke. And low smoke zero hal products, it's the zero halogen that's important. Because if halogen burns, like PVC, that C is chlorine, that's a halogen. ETFE, that F is fluorine, that's a halogen. When they burn, halogens emit toxic smoke and can kill people. So fluoride, there we go, fluoride or chlorine, I just talked about that. So especially in Europe, the European manufacturers are very aware of those gases, and so low smoke, zero halogen products are very popular in Europe. In North America, it isn't engineered in as much as it is in Europe. So you're often, whenever I hear low smoke, zero hal, I'm thinking either it's going to be used in Europe or it's going to be used in North America in tight spaces. So in subway cars, for example, it's used so that if a subway car were to burn, there isn't toxic smoke that will kill people. It's used in shipboard cables for the same thing. If there's any burning, you won't be in danger of the smoke that you would inhale, or at least not in as much danger, excuse me. You're still in danger, but not in as much danger if it's low smoke, zero hal. So whenever you hear that, low smoke, zero hal, either think Europe or an enclosed space. And by the way, think expensive. The cost is higher than a non-low smoke, zero hal application. So just to summarize that, thermoplastic is going to melt. Remember, I said plastic is going to melt. Thermoset will never melt, so it's good for high temperatures. All right, so this is the one to take away. So that's it for the insulations. And now excuse me, low smoke, zero hal, I forgot about that, low toxicity. Okay,
one more topic to go, right?
Yeah, go ahead, yep.
One more topic to go, so probably just a good reminder. If you do have any questions, feel free to use that question window over on the right side and submit those in, and we're going to use any remaining time we have at the end to go through your questions, all right? Thanks, Matt.
All right, so the last topic, and this is not very long, the approval agencies. So the most common here in North America, so is UL and CSA. You're going to hear about those. UL actually is just a private company. It's a not-for-profit organization, so it actually has competitors, believe it or not. There are other folks like ETL is a common one you're going to hear about that competes with UL, whereas in Canada, CSA, while it's a private company, it's specially chartered by the Canadian government. So they own all the approvals in Canada. UL and CSA are very, very similar. They're almost interchangeable, not quite, but if you have UL, generally you have CSA with it. If you have CSA, you have UL with it. Although it gets complicated, and I can talk about that if anyone has any questions. All right. So, excuse me. If ever you look at a piece of wiring cable, if it's UL approved, generally, not always, but generally, it's going to have the UL number on it. And so it's often called the E number. In this case, the IWC has its own UL approval. And so it's E486041. If you were to go to the UL website, you could plug that in and say, oh yeah, IWC does, this is a registered mark of UL. So it means that you can confirm that the manufacturer does have UL. The same thing is true with CSA. Theirs starts with LL. So people might say, what is the LL number? That just means what's the CSA number? What's the E number? What's the UL number? That's all that is, all right? Now, there are a lot of approval agencies out there. And sometimes your engineer is going to come to you and say, we need DNV. Like, DNV, what is that? Or we need CE approval. All I know is that CE means Europe. I don't know it means anything else. So the approval agencies is just this host of acronyms, and each one can be a tip-off for what your engineer is aiming for. And so ISO, most of you are going to know what ISO means, in the International Standards Organization, but some of these others, Keimer, not too many people know that means Holland, or CCC, that's the Chinese mark, and it just goes on and on. So what do you do with something like this? Well, I just want you to, after you learn about who that agency approval is, understand that different agencies have different agendas. So UL is mostly concerned with the question, if this is going to fail, will it fail safely? That's what UL is always addressing. Will it fail safely? UL is about safety. But if you get something designed to the Society of Automotive Engineers, SAE, they're less interested in safety and they're more interested in performance. What they want to know is, can this product meet this amperage application, this voltage application? It's not about will it fail safe, it's will it meet this application. If you have something that's CCC, the China Compulsory Certification, that's really about trade compliance. That's not about safety. It's barely about electrical requirements. They just want to make darn sure that China agrees that this can come into their country. All right? So when your engineer or your drawing or your customer comes to you and says, we need this agency approval, if you can get your hands on what that agency approval means, and actually, well, excuse me, I'll finish that thought. If you can get what that agency approval means, that will be a tip-off to what your customer is really trying to accomplish. Okay, we need it to be CE approved. That means that your customer wants to sell this into Europe. And that's about all it means. It needs to meet these European requirements, but he wants to sell it into Europe. If your customer says it needs CCC approval, all right, that's something going to China. Now, we have prepared a list of about 100 agency approvals by acronym. So if your customer comes back to you and says, we need KEMA-KER, you could look that up under that acronym, and it will help you understand what that agency approval is, and so you can move much more quickly to get your engineers and your customers and your buyers and everyone else a solution to what that agency approval is. All right. And that, by the way, will be available at the end of this webinar. And I believe that's all I have. So any questions now?
Yeah, Matt, thank you so much for sharing your insights. A lot of helpful information in there to help us all get a better grasp of some of the basics of wiring cable. Now, as promised, we did carve out a little time here at the end to do a question and answer session. And throughout the presentation, a few of you have taken advantage of that and put some questions in the window. So once again, we may not have the opportunity to address all the questions live on the call. If not, we will follow up with you directly via email to make sure your question does get answered. So as Matt's reviewing the questions that have been submitted, just allow me that time to just encourage you to go out and explore our all-new website at iwc.com. Some really exciting enhancements that went live back in September for that. For example, for the first time ever, when you go to our site, you'll be able to order online. You'll see pricing and transaction history there for you, and so much more. So that's one thing I'd encourage you to do later on today. And the other thing I'm excited to make you aware of is we also recently released a new ebook that we've published entitled What Every Purchaser Needs to Know About Sourcing Wire and Cable. So if you found value in today's webinar topic, I'm guessing this may be a convenient resource that you'd be interested in downloading and having at your fingertips as well. So as a result, what we're going to do is after this webinar, when you get the follow-up email, is going to include information on a number of things you'll have access to. One is a recording of this webinar. Another is the presentation in PDF format. The third would be what Matt just indicated a moment ago about that master list of about 100 different certification acronyms and what they all mean. And then fourthly will be a link encouraging you to go out and check out this ebook as well. So keep your eyes peeled for that email because there's going to be a lot of helpful information and resources made available to you through it. So enough about us. Let's get to your questions. So Matt, are you ready to jump into our questions that we got from our guests?
I am. Let's go.
All right, great. So first one we're seeing here, if aluminum is so much cheaper than copper, are there new markets where you're seeing aluminum really becoming the conductor of choice and getting substituted in for copper?
Yeah, and this is something that I just touched on, but I'll give another example. It was around battery cables used in cars. Not only then is it the German guys who are doing it, but the North American guys are trying to design in their aluminum cables for cars as well. And it's weight that is driving that. Now there's another example, and this is building wire. I talked about THHN building wire, where the building wire is just used between the walls of any kind of building, and it's always been copper between the walls because aluminum had what I mentioned before. It expands and contracts and expands and contracts, and so aluminum was used for building wire about 30 years ago, and the connections were not so good, and so there were some failures as a result of that. So the NEC went completely away from aluminum, said all building wire needs to be copper. Well, over the 30 years, that has changed. And so now there are some very good connectors that can accommodate aluminum as a conductor. So building wire, THHN, you're going to see more and more of it that is aluminum conductor. And what's driving that is cost. What that means then is that building wire cost will go down in the next 10 years. And it's because aluminum can be substituted now, unlike 30 years ago when it couldn't.
Okay, great. A few more questions that come in. Another one from the audience. Is the wire and cable industry, are you seeing a higher demand for higher temperature, high performing insulations? Examples would be Teflon or a new material like PEEK.
Yeah, it's a great question. The answer is absolutely, absolutely. So the demand for the higher temperature and higher performance, they're not always the same, but it continues to grow. And let me give you an example. PEEK is a perfect example. That's a very special kind of insulation that is used for high temperature. I believe it's thermoplastic. I don't believe it's Thermoset. Another example is all the polyurethanes that are being used, and that's just something where the Americans are borrowing from the European playbook. Polyurethane is an incredibly hard abrasion resistance insulation that the Europeans have been using for years, and the Americans didn't like it because it was too doggone expensive. Well, what Americans learned was that even though it's expensive, that cable lasts a much longer time. And so the market is moving toward a higher performance insulation. In this case, it would be polyurethane. With regard to higher temperature, yes, the insulations get higher and higher rated. Every 5 years or so, you see a jump in product. So PEEK is an example of a product that can accept a higher temperature. There's another one that is escaping me right now that is called out all the time on the drawings. I'm having a senior moment here. But to be sure, higher performing insulations will continue to grow. Yes.
All right. Great. A few more questions in the time we have here. So it looks like somebody was observant when you're walking through the different plating materials. The question was, isn't nickel cheaper than silver? So why would you use silver instead of nickel at that 200, 250 degree temperature when nickel could do it as well?
Yeah, that's a good question. And actually that comes up often. There was one of our salesmen asked me the very same question, and the answer is yes, nickel is cheaper than silver. It's a lot cheaper than silver, but it's expensive to plate. It's difficult to put onto the copper, and also the environmental controls around nickel, since it's a heavy metal, are considerably more expensive. So nickel-plated copper is more expensive than silver-plated copper, not because of the base product is more expensive, but because applying it is more expensive.
Interesting. All right. Well, Matt, we had a few more questions roll in here. We'll try and get through as many as we can. So next one here, we hear much about 60-degree wire, 90-degree wire, et cetera. Can you help explain those terms and where those wires are used?
Oh, yeah, sure. So PVC can be rated for 60 degrees, 75, 90, or 105. There are 4 different grades of PVC. The higher you go, the more expensive it becomes. So you might have designed a 60-degree PVC. That is commonly used for consumer stuff. If you go to the hardware store, it'll commonly be rated for 60 degrees. But if you're going to be using a PVC in an engineered application, generally your engineer is going to, and by engineered I mean specially designed for an application. Generally, that's going to be at a higher temperature. So your engineer might say, I need it to be 105 degree, or I need it to be 90 degree. Every time you hear that, just hear expense. The cost goes up as you go up. All right. Thermoset materials can be the same, by the way. Rubber that is used in most rubber cables is rated at 90 degrees, but you can get it rated at 105. You can get it rated at 125 and 150. Same thing. As temperature goes up, cost goes up.
All right. Looks like we have time for one more question here. Insulations are often marked with terms like VW1 or FT1. Can you help explain what those mean?
Yeah. So if you read the legend on the conductor that you have, and most UL products have the legend on them, not all. It isn't required on all, but the majority have to be labeled. And you see VW1 or FT1. That's just a flame test rating. All it means is that it's passed a rigorous flame test. VW1 is a vertical flame test. That means that the cable is literally held up and down, and you light it at the bottom, and you know that flame wants to travel right up that conductor and has to extinguish itself within a certain distance. FT1 is the very same thing, but it's the Canadian version, the CSA version. So if ever you see those markings, they all mean something, and you have to go to your engineer or to your wiring cable specialist to explain what the heck it means.
Great. So thank you, Matt, for answering these questions submitted. Thanks to everybody who did submit their questions. We appreciate it. That takes us to the end of the time we have for today's call. So thanks again to all of you on the line, our valued customers and partners who joined us today. Of course, thank you as well to our presenter, Matt. Hope you found this to be practical, informative, and we really would value your feedback. So there's going to be an online survey that's going to launch and be available to you immediately after this webinar session closes. If you can take the 3 to 4 minutes to complete that, it'd be greatly appreciated. And lastly, just please remember, watch for that email in the upcoming days. We're going to share a whole lot of valuable information with you, recording of the webinar, PDF of the presentation, that agency listing form, as well as a link to download that new ebook we discussed. So keep your eyes peeled for that email and have a great rest of your day. Thank you.